First of all, I would like to welcome everyone joining us today on a Saturday morning. It's a rainy day, so it should be time well spent. And I would like to welcome Ed for joining us today and walking us through that hopefully not too complicated new tool connecting Rhino to PHP and Wolfie passive. Certainly something which hopefully is a good tool. I was hoping that some of my students will join because we use Rhino, of course, in school, and I'm very curious to see how it works. So Ed,
Sure.
let's take it away.
Absolutely. All right. Sure. Thanks, Andreas. And yeah, thanks to New York Passive House for inviting me to present here this morning. And thanks for all your work organizing the symposium here. So yeah, it's great to see everybody on this rainy Saturday morning. Glad you're able to come out for this, and hopefully this will be of some interest to you. I'll do like a quick 15-20 minute introduction to like what it is that I'm talking about here. And then mostly what I wanted to do with today's session was sort of do some live modeling so that you can really see how the workflow works and sort of what the setup looks like in a sort of real world application. And then obviously it's a nice smallish group here. So if you guys have questions or thoughts, feel free to unmute yourself and voice those at any time. Always love to hear any thoughts or questions that you might have there. So the software that we're going to demonstrate, or that I'll be talking about today, is this Honeybee PH software package. Honeybee PH is a plugin which we have developed within our office to help us connect lots of different building information models, but in particular Rhino, to the Passive House modeling tools, both PHP and Woofy Passive. So both of those can now be connected to various different building information modeling platforms. As I said, the one that we like the most, and the one that's probably the most well developed, the one that we use for all of our work in the office, is Rhino. So Rhino 3D with its associated Grasshopper parametric modeling platform, we find to be a really good information management and 3D modeling tool. So we're using that for pretty much all of our work, pushing that out to, again, both PHP and Woofy Passive. So briefly, why have we developed something like this? What is the sort of goal behind something like this? Broadly, from a sort of really basic perspective, we find the Passive House modeling tools to be super effective evaluating and simulating annual energy consumption of buildings. We find the Passive House frameworks to be really useful for our projects, and we find the modeling tools to be really useful when evaluating operational energy consumption, which of course is the basic building block that we need if we're going to be modeling total carbon emission footprint. So the operational energy is a core piece of that. And we like these tools very much. However, there are not very many good information modeling or 3D modeling front ends for these tools. There are some, both Woofy Passive and PHP have a SketchUp-based interface. But we don't like those tools very much. We find them lacking in all sorts of areas. I mean, the development on them is great. The teams developing them are amazing, of course. But they are both very, very incomplete, both on the Woofy Passive side and the PHP side. Neither one offers a complete solution. And sort of fundamentally, while SketchUp is a neat drawing tool, it's a very, very poor information management tool. So if our goal is to build out a really robust building information model with all sorts of rich data associated and embedded, managed within the model, SketchUp is a very, very poor tool for that, for all sorts of reasons. And so we like Rhino as a platform. We like it as a 3D modeling tool. We especially like it as an information modeling tool. And so being able to connect that to our Passive House energy models is hugely beneficial to us in terms of overall project workflow and overall performance. And so what we were really trying to do, the sort of fundamental question that we were trying to ask many years ago when we set out on this sort of development process, was was it possible to build a set of tooling that would enable us to connect our building information model of choice, again, in this case happens to be Rhino, but to connect our building information model of choice to the Passive House model make all of those connections between the data points, and then really just get out of our way so that we can stop spending so much time and attention on modeling and focus more of our time on evaluating results and really designing better buildings. What we have found over the years working in the passive house space is that we just spend so much time on the nitty-gritty modeling phase that we end up sacrificing the time, energy, attention, and fee that could be better spent on actually optimizing and improving people's buildings. So that's really what we're after here, is tools that work well and get out of our way so that we can go back to the important work of engineering better buildings. So that's our sort of basic intent here with a lot of these tools. So we'll talk a little bit about like the sort of basic structure of how the tool chain is put together. And then, as I said, we'll kind of dive into some live modeling, excuse me, live modeling together to kind of show how it all works. The first piece of the puzzle to understand, or the first piece to recognize here, is what we call the Passive House Exchange software library. So the very first piece of the puzzle that we built out was what's known as an API, an application program interface, which allows us to move data in and out of the proprietary passive house modeling tools. Again, we're talking here about PHPP and Woofy Passive. So those two energy modeling tools, which are very good for evaluating annual energy consumption, both have very, very challenging interfaces. It's very difficult to actually build models within them. You know, they're great calculators, but it's very, very hard to build models within those platforms. So what we wanted to do is be able to build our models somewhere else and then push the model data in, execute the calculation, and then read the result data out. So we developed what we call the PHX, or the Passive House Exchange API, which allows us to do just that, to move data in and out of these passive house modeling tools. Now, what does that look like? What is the PHX? Well, it kind of looks like this. It's a software library. It's a sort of series of code libraries which are combined together in a certain way to allow us to write and read data from those software packages. But obviously, we don't want to use this type of tooling on a daily basis for our energy modeling purposes, right? This is important, but like this is not how we want to work on actual projects on a daily basis. So what we had to do at that point was figure out an interface for the interface. We had this API, this application programming interface, but we needed some sort of tooling or platform that would allow us to build our energy models in a more typical architectural modeling or building energy modeling fashion, right? We needed a 3D modeling engine, and we needed some sort of platform to work on top of there. So the interface for the interface, the sort of front end, as it were, the tool that we chose to use to build up these passive house models before the data gets pushed into Woofy Passive and PHPP, was the Ladybug Tools platform, in particular, the Honeybee Annual Energy Calculator. Now, if you're not familiar, the names sound a little funny, I know, that this is a series of software libraries and a software platform, which is widely used within the sustainability and building energy modeling universe. This tool, this framework, is not designed by us. It's not built by us. This is somebody else's platform made by the Ladybug Tools team. And what we decided to do was try and utilize as much of their platform as possible, and then build our new passive house modeling tools on top of it. So our tools here, the Honeybee PH, is a plugin for the existing Honeybee and Ladybug tools. So it's an add-on, as it were, in order to allow us to do specialist passive house modeling while we build our Ladybug and Honeybee models. So the basic idea there is that you build up your Honeybee or Ladybug tools energy model in whatever tool of choice you are working in. So The Ladybug tools allows us to model in Rhino, of course, but also in things like Revit and SketchUp, as well as using the Open Studio engine there. But it also has some really impressive and robust connectors to things like IES. Nowadays, I think it can also do eQuest. I think it's got an eQuest connection as well. So there's all sorts of different connectors that the Ladybug Tools toolkit has. And so by building on top of it, that allows us access to all of those platforms as well. The other thing to say is that the Ladybug Tools ecosystem is designed to connect to all sorts of different analytical models or calculators. For instance, we might use the Honeybee model to do detailed hourly energy assessment. We might use it to do detailed thermal comfort assessment or daylighting assessment. And now with the addition of the Honeybee pH toolkit, we can also use the same model for our Passive House annual energy assessment and certification assessment. So we can now use that one model for all sorts of different purposes, which significantly streamlines and improves the overall workflow that we're seeing. Because a typical project might want to execute all of those for different reasons at different phases of its lifespan or time frame. So again, the Honeybee pH was designed as a plugin. So Honeybee itself is responsible for geometry modeling and visualizations. And then it has a series of different plugins that do different things. So specifically, there's the most well-known ones would be Honeybee Energy. Honeybee Energy is the plugin that allows us to do Energy Plus modeling. So detailed envelope assignments, HVAC system modeling, thermal comfort calculations, hourly energy and load calculations for our buildings. By contrast, there's another plugin, which is known as Honeybee Radiance, that does detailed daylighting simulations using the Radiance engine. And now, as I said, we have this Honeybee pH as a new plugin that allows us to bridge between the Honeybee model and our specialist Passive House modeling tools. So that's the sort of basic intent and structure behind the tooling that we have been working on here. And that's what we're going to sort of show today. And so the sort of basic workflow here is that we model and build our building information and building energy models using, again, whatever tool we want. So whether that's Rhino or SketchUp or Revit or whatever, Vectorworks, whatever sort of tooling you might be using. So those different tools support different levels of user input, right? So we can build out our models to different levels of resolution with the different tools. Some are better than others, and I would say the most well-developed, of course, is Rhino. That's the one that we'll be showing today. That data is then used to build up a detailed Honeybee and now Honeybee pH model. The model data is then passed off to the Passive House Exchange. Passive House Exchange manages all of the data in and data out of those Passive House modeling tools. So that's the sort of basic tool chain there. All of this is open source. All of this is free. The downside to all of this, the biggest downside, is that you can sort of see it in the chain here, is just the number of different pieces of software which are being connected together. So in order to utilize these libraries, you have to know your building information modeling tool. So maybe Rhino, let's say in this case, you need to know all the kind of ins and outs of Rhino and in particular the Grasshopper modeling environment, which is a complicated sort of thing in its own right. You need to know or understand the Honeybee modeling process, which is like a whole other set of nomenclature and tools and processes. Then there's the Honeybee pH specific tools and components that need to be understood. And then there's the Passive House models, which need to be understood. So there's like a very steep learning curve here, just because there's so many different pieces all connected together. So again, very powerful, offers a lot of flexibility, but certainly does have a very steep learning curve. No doubt about that. But we'll try and make that a little bit easier here today by demonstrating some of the basic workflow. Now, I'm going to demonstrate the basic workflow for a specific 3D modeling and building information modeling package named Rhino 3D. Rhino 3D is just one of many tools that you might choose to use. It is certainly the tool that we like best, and it's the one that we've built out the most tools for. But it's important to note that all of the Honeybee pH and Passive House Exchange software is platform agnostic. That is to say, it works with anything that can create a Honeybee model. So you are not locked into one or another information modeling platform, Revit, Rhino, what have you. So you can use whichever one that you like. That said, there are a lot of benefits to Rhino, and as I said, we built out a lot of custom tooling for Rhino in order to make the Rhino process much simpler and more straightforward. As I mentioned, we use this platform for everything within our office. So, we as professional Passive House consultants, consult on, 60, 70 projects a year. And all of them are modeled using this platform. So whether we're talking about single family homes, whether we're talking about townhouse retrofits, or whether we're talking about multifamily buildings, whether we're talking about PHPP or Woofy Passive, all of that is modeled using this tool and this platform. So all of that work flows through these tools within our own office. Here, this is just a screenshot of a in-process multifamily project, which is achieving the FIA certification using the Woofy Passive modeling. And you can sort of see in the layer list to the right, the number of different things that we're able to model using this platform. So of course, the geometry, that's sort of table stakes, right? That's the same way that we might model geometry using the SketchUp tools. We have to be able to model the detailed building geometry, as well as all of the various components and assemblies that are used on the building. But importantly, with a tool like this, we're able to also model things like the mechanical systems, all of the ducting, all of the ERV and heat pump units, all of the hot water piping, down to a very, very high level of resolution, all the thermal bridges, all the detailed shading. We'll sort of talk about different options for doing advanced shading and solar radiation calculations, as well as all the internal loads and programs. So things like lighting, ventilation flow rates and schedules, all of that can be managed within this single platform, which we like very much, especially for bigger, more complicated buildings where those types of internal loads are super, super important. So we have definitely found that to be really helpful in the type of modeling work that we're doing. Now, specifically, why do we find that helpful? Just very briefly, if you are not already familiar with the Rhino Grasshopper universe, if that's new to you, Rhino, the 3D modeling tool, has a sort of sister application known as Grasshopper, which I know it's funny names, but the Grasshopper tool is used for what they call visual scripting, which allows us to build up these definitions of functions in order to manipulate the 3D model. So we can write to the 3D model and also read from the 3D model. We can assign data to different geometry elements in the 3D model, and then read that data back at a later time. This platform allows us to build up these detailed building information and building energy models very, very efficiently, and very, very flexibly as well, and then use them for all sorts of different purposes. So we like this this kind of hybrid platform a lot. It's a little weird. There's not very many like software applications I can think of that have this structure where there's like two applications that are like glued together, sort of. But Rhino, that's the way it works, and it has worked very well for us in that regard. Just in terms of the sort of pieces of the puzzle here that currently exist, so that we have all sorts of tools in Rhino for managing assemblies and geometry, of course, as we said, all the different components like windows, thermal bridges, detailed shading. So we'll talk about some of the options there, and then things like treated floor area, internal floor areas, of course, just like you might get from, let's say, Design PH or the Woofy Passive SketchUp tool. But as I said, in addition, we have all sorts of specialist tools to do things like hot water and mechanicals, all the detailed appliances and plug loads, programs, which of course are super important when we get to bigger buildings or non-residential use types. And then even to things like managing the variance worksheet in the PHPP, automatic PDF outputting for certification purposes, et cetera. So there's all sorts of different tools there, and we'll, as I said, look at a few of them today as we go. So those are just a few examples there of some of the different tools that we have available to us. The Honeybee PH tool is all free and open source, and you can download it from passivhaustools.com. So going to passivhaustools.com, you can get your hands on the software there. As I said, all free, open source. This is a project, not a product. So this is not something which is being sold, simply something which we are building and happy to share with the Passive House community if it is helpful for you in your modeling work. So okay, so hopefully that's a helpful introduction to the tools and just kind of the basic groundwork. What I'd like to do with the next maybe hour and 20 minutes, whatever, however much time we have here today, is go through a few in-person kind of live modeling examples, and we'll take a look at some of the basic tools and the basic workflow. So we'll take a look at a very basic model, exporting to Woofy Passive. We'll talk about evaluating performance of the buildings. How do we use something like Woofy Passive to evaluate performance of the building? We'll talk about some typical, and then what we'll do is talk about some typical improvement strategies. So, based on what we see in those energy models, if we wanted to improve our overall modeling, how could we do that? Or model performance, how could we do that? So looking at things like envelope improvements, R values, windows, looking at mechanical system improvements, and then we'll take a detailed look, or if we have time, we will dive into some of the different options for looking at shading as well. So we'll take a look at a bunch of those.
There's a quick question by Kevin. Are you working with many firms tied into the Revit world?
That's a great question, Kevin. The short answer is no. Surprisingly few of the teams that we work with are working in Revit right now, which is very interesting. And I would follow that up by saying even the teams that are working in Revit, what we have found is that we typically prefer to simply export flat CAD drawings and build up our building information model ourselves. What we find with almost all of the Revit models that we get is that while they are designed in order to produce the architectural drawings, and they make very nice architectural drawings, the models themselves are often surprisingly messy, let's just say. And so it becomes very hard to extract the information that we need from them. And we continue to find that it's just faster and easier for us to build up the energy models based on flat CAD drawings. Now, we don't want that to be the case. And hopefully someday we can move to a world where we're able to pull that data in more cleanly, but we have not had any success with that so far. So we continue to just, even when we get Revit models, we just export DXFs and then we rebuild the energy model ourselves. The energy model is just so different than the architectural model that it's all but for us, it's been all but impossible to cleanly translate one to the other. That said, there are some really interesting examples of teams working on that problem. I mean, the Ladybug Tools team is probably the best sort of example I can think of. Those folks have been working for many years now to make really good Revit side tools to build up Honeybee models from Revit. But even so, even with a whole team of professional software developers and some of the smartest energy modeling software developers around and years of development, it still takes a lot of kind of monkeying around. There's kind of some workarounds. They use rooms, like the room elements in Revit instead of the actual envelope elements in a lot of places. There's like a lot of workarounds that you have to do, and it's in many cases a pretty gnarly process. That said, they're doing an amazing job with it, and it's amazing that they have as much tooling as they have there. but it is by no means a one-click operation to like, export model to building energy model. It still takes a lot of input. Kevin says the sloppiness of Revit models and the nervousness of the people responsible for maintaining files is becoming apparent. Yes. Yeah, I think it's a bigger discussion, but fundamentally I think the issue is that the model builders are charged with making PDF drawings. Right? That's the purpose of the model until we get to a scenario where the model is the deliverable. The models will continue to be kind of messy and full of drafting views and wipeouts and overlays and all sorts of workarounds. And fundamentally, that's because the model itself is not the deliverable. The PDF drawing set is the deliverable. I think that's my supposition there. I could be wrong on all that, though, of course. What we're going to do. So I just stopped sharing my screen. Actually, hopefully you guys can still see my screen, right? It should be just gray right now. Okay. So what we're going to do now is I'm going to open up Rhino and we're going to look at a couple examples together, and we'll kind of talk through some of the basic sort of workflows here. So as I said, if you want to get if you want to get this tool, again, it's all free, open source, just a software project that we've been building out. So you're more than welcome to. We would love it if you give it a try and let us know what you think. The easiest way to do that is to go here to this passivehousetools.com. So passivehousetools.com is going to be the easiest way. There are other ways to get it, but that's probably the most straightforward. So if you go to passivehousetools.com and down here under the various tools, you'll see there's a couple of different ones here, but the one that we're interested in here in today is Honeybee PH. So Honeybee PH is going to be the general toolkit that we're going to use for our purposes here today. So Honeybee PH, you can see the Honeybee PH website here with all sorts of different information. You can see the installer, so the installer file here, and up at the top here you can find some links to some other elements here. So there's a sort of installation helper if you need help with installing the software, a sort of quick start guide, and then some other learning resources here. For our purposes here today, if you are interested in following along and you kind of want to model along with me, if you go to this Learn More and come down here to this Parsons Regenerative Metropolis, I have put the source file for the stuff that we're going to go over today right here on the website, so you can kind of just grab that from the website here, so you can download that. So I'll just grab that, bring it to my desktop here, and if you unzip it, all it's going to be is a Grasshopper file. So everything's in this one Grasshopper file. So again, if you want to follow along, you're welcome to. You can go to the passivehousetools.com, navigate to, again, the Learn More, and then on Learn More, we have this workshop link here, and then there's a big button here that you could download the files. I see in the chat there, Justin agrees. It's always better to create separate 3D model for Passivhaus output. Yeah, that's certainly been our experience. Justin says you need Rhino 7 to make it work. That's correct. So this will only work on Rhino 7 or above. So Rhino 7 or above. We are not 100% sure if it works on Rhino 8 just yet. We're still testing out whether or not it will. We're updating that right now. Obviously, Rhino 8 is only in beta release, but obviously we'll test everything and upgrade it for Rhino 8 at some point. But you're right, Justin. That's correct. So we need Rhino 7 for this to work right now. So okay, so if you and thanks Andreas for putting the link in there. So again, you can download this Grasshopper file if you want to follow along, but you certainly do not have to follow along. We'll kind of demonstrate everything here today. So I'm going to bring up Rhino. I'm going to be working on a Mac, but you could be working on a PC. It's up to you, whatever platform you want to work on. We are going to be exporting to Woofy Passive. And so for that purpose, I will be using Parallels on the Mac in order to run Woofy Passive as well, because that only works on Windows OS. So, just to add a little more complexity and sort of weirdness to the whole thing. But let's take a look at the model. Let's take a look at the model, and then we can talk about all of that nitty gritty as we get into it. So I'm in Rhino here, and I want to open up this Grasshopper file. So the first thing I'm going to do is come over here, and I'm going to choose a template with inches as the unit. This is not important for Honeybee PH. It's merely important for the Grasshopper file here, the sample file. That's in inches. So if you open it up in a different unit format, you'll just have a different size building. That's all. So I'm going to open up an inches template. So I'm just going to double click on that, and I can double check that by just typing in units here. And I can see that my units are in inches. Again, if you're not familiar with the Mac version of Rhino, this might look a little weird, but for those of you who are, hopefully it's pretty straightforward. So this is my Rhino application. This is my application that I can model in, right? So I have my modeling environment here that allows me to model my geometry. We're not going to be modeling geometry in this environment, though. Instead, we're going to be using the Grasshopper platform. So so the way that I open that is by coming up here to this Launch Grasshopper, and I'll just click Launch Grasshopper here. And then I'm simply going to take my file that I downloaded and drag it over here and drop it, and it'll take a second to just go off and open up. And the only reason I did this was just to make this session a little simpler, to create this sample file that we can start from, so that we don't have to start from absolute zero and sort of build up an entire model. So there's some geometry embedded in this Grasshopper file. There's some other bits and pieces there that are sort of built in, just to, again, make things a little simpler for this session, just so that we don't spend a ton of time, waste a ton of time going through that kind of stuff. So let me just do a little bit of rearranging here so that we can see what we're up to. I'll do this. Okay. So on my left here, I have my Rhino window, and on my right, I have my Grasshopper window. And as I said, Grasshopper is a visual scripting tool, which allows us to combine together different nodes, different functions in order to execute some operation. So fundamentally, what we're doing here is building our energy model, and then we're going to export the energy model data out to Woofy Passive. Right? Those are the two steps: build the energy model and then export the energy model out to Woofy Passive, where we will review and inspect the results. So you can see on the right here, I'll zoom in a little bit. You can see on the right here that we have a couple different phases that we go through when we build our model. We build up the geometry of the model. We build up and define the interior spaces of the model. We're going to build up and define the mechanical systems, the shading, and then lastly, we're going to export the model to Woofy Passive. So you can kind of imagine this as an English language book where we might read from left to right. So the data is going to flow from left to right. So we take a bunch of data in on the left, we execute a series of permutations and add a bunch of attributes and define a bunch of elements. And then on the very right-hand side, we export it out to another tool. In this case, Woofy Passive is the one that we'll take a look at today. So there's a couple things we can do just before we get any further than this. Let's just take a look at the building in question. And to do that, I'm going to use a honeybee tool. So up at the top of here, you can see that I have a whole series of different tools. I've got my maths and vectors and curves and whatnot. I also have a tab here named honeybee. So these are the native honeybee modeling tools. Remember, honeybee is responsible for geometry creation and visualizations. I have another one over here, which is labeled Honeybee Energy. So this would be the toolkit, which is responsible for detailed hourly energy consumption, as well as thermal comfort, and to limited daylighting assessment as well. We have our Honeybee Radiance, which is the toolkit dedicated to daylight simulation. And then, as I said, we have our new Honeybee pH toolkit here, which is responsible for all of our energy consumption. So, excuse me, our passive house modeling in order to assess our annual energy consumption. So lots of different tools. Each one of these tools here responsible for a different piece of the puzzle. Each one here a different function to do something. Build a branch pipe, build a fixture pipe, build a trunk pipe, etc. So we kind of click all these pieces together in order to build up our overall model. But to go back, we wanted to just take a brief look at the building here that we are working on today. So to do that, I'm going to go to Honeybee. And remember, Honeybee is responsible for visualization. So if I come here to visualization, there's a bunch of different visualization components that I might use, but I might choose this one here, which is called Visualize by Type. And all this is going to do is allow us to see the building that we're working with. So we're just going to be able to see that a little more clearly. And I see Alex has a question there. Is this the same for PHPP? And the answer is absolutely yes. Yep. So the only difference The only difference for the PHPP process is that instead of exporting to Woofy passive, you export to PHPP. Other than that, everything is identical up until the very last step. You choose which software you want to go to. So great question. So anyway, I'm going to come here to visualize. I'm going to say visualize by type. I'm going to click on this, and then I'm going to drop this component onto the canvas. And you can see here, I get this little component that floats around on the canvas. What does this component do? It's also giving me this little warning here, and it's showing up yellow. It's obviously not really working, but it's just not getting any data. So as I said, this whole thing works like an English language book. Data comes in from the left, data flows out to the right. Notice here that this little guy has a connection on the left, but it's currently not connected to anything. So that's quite straightforward. All I'm going to do is come up here, grab my model. I'm going to click and hold with the mouse, and then I'm going to make this connection. And I just make the connection by connecting it here and then releasing. And as soon as I do that, what you'll see is that a preview of the building pops up into existence here. So this building, the geometry for this building lives inside of this Grasshopper tool. And right now we're just visualizing it using this component. If I delete this component, I have not deleted the geometry. I can always come back and I can put that component back onto the canvas, remake the connection, and my building pops back up, right? So this is just a visualization tool. This is not actually building any geometry. The geometry itself is defined much earlier, way over here in this zone geometry input. So just an important distinction there. So this is the building that we're going to be working on. It's a very simple little single family home. Primarily the intent there is just for us not to get lost in the geometry and the form. We just want a really simple project that we can then look into the tooling here on and kind of investigate the different pieces, right? So little single family home, 2 stories, little gable roof, some south facing glazing. That's good enough for us to kind of walk through the workflow here. So again, let's kind of take a look at these things in a little more depth here. So first of all, the first step is to build up the geometry. So these yellow zones. So I have some geometry that comes in. I build up the different rooms. I have some windows that come in. I build up the windows. The windows get hosted onto the geometry. That's this whole piece in the beginning here is just putting the different pieces of 3D geometry together. In this example case, the geometry is embedded in the Rhino file. In a real world case, your geometry would probably be in the Rhino file, and you'd be building up that geometry. That would be part of the modeling process, would be actually constructing the 3D geometry. So lots of different ways that you can kind of manage that. But in one way or another, you're going to bring the geometry in, and you're going to build up the building energy model zones. So what we get from all of this is a series of building energy model zones. In this case, it happens to be these just yellow rectangles, but obviously in a more complicated project, you'd have much more complex and more detailed zones. Now that's going to help us, or that's going to allow us to define the outer surfaces of the building, the exterior envelope of the building, as it were. When it comes to the interior spaces of the building, we're going to define those a bit differently. So we have a set of tools here, or a little chunk here, which allows us to build up what are called internal spaces. The internal spaces can be thought of as rooms. They don't always map to individual rooms. Sometimes they might be a whole apartment or something, but for the most part, they would be individual rooms. So internal spaces. The internal spaces have all sorts of data points associated. Most importantly, they're going to have things like fresh air ventilation flow rates. So you might say, oh, the kitchen has 50 CFM of airflow. The bathroom has 25 CFM of airflow. And then other program-related items like lighting, electric appliance, energy consumption, occupancy, and other use-related specifications. So those kind of internal uses get assigned at the space level. You say, oh, the hallway has 0.5 people per square foot. The lobby has 2 people per square foot, or whatever the number would be. So all of that gets defined for the interior spaces. Once those loads and schedules have been assigned, we can then build out our mechanical systems. So you can see here that we're building up some mechanical systems, and then the mechanical systems are getting applied to those thermal model zones. So we build up an ERV, we build up a heating heat pump and a cooling heat pump, and then all of those get assigned to the thermal zones there as well. So we can build up mechanical systems. Now we can build up very complicated mechanical systems. Here we've just got a really simple one, again, just to kind of get everything working and let us build up all the connections. We're going to set some site and climate related elements over here. And then we'll add in some shading. And then lastly, we're going to export everything out to Woofy Passive. So we're going to export everything here to some sort of calculator, right? So this Grasshopper tool is not doing any calculation itself. All it is doing is building up the energy model. So it's defining attributes. It is allowing us to create systems like the mechanical system, and then assign those to different thermal zones. And then when it's done, what we're going to do is export the model out to Woofy Passive. And that's fairly straightforward. And again, to Alex's question, would this be the same for PHPP? Yes, all we would do, instead of using this component to write it out to Woofy Passive, come up here to our Passive House tools, we would instead use this one to write out to PHPP. So other than that, it's all the same, right? We use the same energy model construction process. The Woofy Passive will be a little easier for us to work with here today. So that's the one we're going to use for this particular session. Questions on anything there before we jump into the next? So Caleb says, if you wanted to export to IES or Energy Plus, you would swap out to Honeybee. Oh, yeah, exactly. So for instance, so at this point, at this component right here, what I have is an energy model. What I could choose to do would be, it's a great question. What I could choose to do would be to come up here to Honeybee Energy, grab my model to Open Studio, take the same model and pass it over to Open Studio Energy Plus. So the exact same energy model or geometry and attribute model can then be passed to various different calculators, depending on what you want. If you want to do thermal comfort, if you want to do daylight assessment, if you want to do detailed hourly energy performance, or if you want to do passive house annual energy performance and certification assessment, right? So lots of different things that you might use this one model for. That's a great point. So we can do all sorts of things with this. We could also alternatively use our radiance tools here to calculate our daylight. You know, if we were doing an interior daylighting assessment, we've also got some thermal comfort tools baked in here with Honeybee. So this one model can branch off to various different places.
Ed, very quickly,
Please.
The little pipelines you're building between different components here, are they both ways? They work both ways, or is it better to think about it downstream only?
Good question. That is a great question. So it is downstream only. So it is a one-way passing of data. It's a really important and great point. Thank you. So the data flows from here. So this little component takes in, do it this way. This little component takes in some data. It does some stuff to it. It sets the climate, and then it hands off the data to the next link in the chain. The data does not ever flow backwards. So after something has been modified, it does not then sort of flow back to the sort of origin point there. So you're sort of making modifications and edits and changes as you go along there, but it doesn't ever flow backwards.
A quick follow-up to that. So if you make upstream changes, then do you, in Design PH, you have to hit export, and then you got to import a PPP file, and you got to do all that. So in this case, if you make changes in something in some part of the chain, does it automatically update the energy model? Now I imagine like at least upstream to the export to Woofy Passive or PHPP or IES or whatever. Upstream of that, does it then update everything downstream from your original model? Or do you have to, do an export thing again?
So PHPP, yes. So for PHPP, the tooling here will continuously write to the PHPP document. So if you make a change, it will automatically propagate through into PHPP. For Woofy Passive, no. So for Woofy Passive, you'll see in a second, we'll kind of show that. For Woofy Passive, we have to do kind of the design PH thing where we export out a file and then we open it in Woofy Passive. And there's no sort of connection there. There's no automatic updating, unfortunately. So for PHPP, yes. For Woofy Passive, no. Just to make the answer as complicated as possible. It's a great question, though. So Alex says, theoretically, you could add materials and export to an embodied carbon tool. Exactly. You're exactly right, Alex. Right. So this model right here is completely software agnostic. This model does not care whether it's in Rhino or Revit or being used for thermal comfort simulation or being used for passive house simulation or whatever. It's just a model with a bunch of data. You then pass that model off to whatever calculator you want to use for whatever it is that you're investigating. Could be passive house certification, could be daylighting, could be thermal comfort, could be hourly energy, could be carbon assessment, carbon emissions assessment. So that's exactly right, right? So we're just building up this model, but this model is software agnostic, calculator agnostic. It is just a description of the building. We can then use that to do whatever we want to it.
I have a question about the shading.
Please.
So when you're creating a shading model here, I saw that shown on your screen. Does it, are you describing actual 3D geometry of surrounding context? Or are you doing something where you have to manually describe like the 6 columns in the shading tab of the PHPP?
Great question. So, so you are simply modeling the actual geometry in the 3D modeling environment. And then the tool here is going to do all of that tabulation and calculation. So it'll determine all of those dimension out, dimension up, dimension side, but it'll do that based on actual 3D geometry in the scene. So all you have to do is build your geometry.
Would you funnel it into Design PH, or is this a way to like bypass Design PH and get the same information into the PHPP?
You could do either. You could do either one. So you could do either one. Okay. So we'll talk about there are 2 different shading calculations built into this toolkit, and then it supports some other workflows as well. So depending on what you want to do, there's actually quite a lot of flexibility there. I think that there's the capacity here to bypass Design PH entirely. That is not allowed at all for PHPP or Passive House Institute certification right now. So for that purpose, we've built in the more basic shading tabulation tools as well. But potentially in the future, we could shift to this alternative model. But that's a bigger discussion, and it involves the certification rules and all of that kind of stuff.
So you could
we at least have the technical capability.
Could have it export to Design PH, the parts that Design PH can do. And if you're doing something more intricate, like a shading screen or something, you could and analyze that in a different way.
Exactly. Yeah. So we have the technical ability to do many different types of assessments. The rules say we can only do it one way, so that's fine. So we built in tools for that, but there are a bunch of other options here, and I'll show those. I'll show some sort of real world examples of what that means in a little bit. So yeah, you betcha. It's great question. Justin wants to know, where do you assign the specific information for each surface? So TFA, adiabatic, outdoor surface. We'll look at that, Justin. Hold on. That's a great question. It'll be different for exterior surfaces versus interior, but I will show that. So one of the optimizations we're going to do here is improve the thermal performance of the insulation. So we'll look at that in just a few moments, and we'll sort of touch on exactly how that works. Great question. Let me clean up my, let me clean this up a little bit here. Other thoughts or questions before we take a look at the Woofy export? All right, so I'm going to export this out to Woofy. Again, this would be the same, similar, basically the same if we were going to PHPP. So I've got my export here. There's 2 steps that we have to go through. We're going to write out the model data to a text file. It's a very simple, very stupid text file. We'll take a look at it. It's not scary. It's just a text file. It's a text description of the building. Then we're going to take that text file and we're going to convert it to a Woofy file. So those are the 2 steps that we go through here. In order to do that, I just need to save it somewhere. So I'm going to come up here and I'm going to right click with my mouse, and I'm just going to say that we're going to save all this stuff to my desktop just to keep it easy in this session. Obviously, for a real project, you'd probably want to save it to a project folder or something. But I'm just going to save this all to my desktop. So when I'm happy with this, all I need to do is set this to run. So I double click on this little guy here, this little switch. See, it goes from false to true. This guy's going to go off and write to a text file. This guy's going to go off and write to a Woofy file. And then when I'm done, I can turn this off. These guys are now no longer writing out to file. So what just happened? So something happened, but we're not sure what just happened. I'll come over here to my desktop. So what just happened was we created 2 files. Let me put this one over here. Get rid of this one. So we created 2 files. We created a text file of the building, a text file description of the building. That was this first component. So you see HBJSON file, HBJSON file. I'll talk about what that is in a second. And then we created this Woofy XML file. So this is an XML file. So let's take a look at this one first. I'm just going to open this up in a simple text editor. So I'm going to open it up in a text editor and we'll kind of take a look at what this is. So I just opened up this file right here. Now it might look a little bit scary at first, but I promise it's not. Let me do this. I'm just gonna roll it all up and we'll look at it kind of one piece at a time. It's just a text file. It's just a text description of the building with all of the elements in here. So, and we can kind of read it, right? It's all in English language. The units of the model are inches. The display name of the model is whole building. Where did it get that from? Well, if we come back over here, you can see that I named it whole building, right? And so if I change this to another building and I rerun the export, come back to my text file, roll it up. Notice here that it's now called another building. So it's very, very there's no magic here. All it's doing is making a text description of the building. And there's all sorts of data embedded here. So we have each of the thermal zones, and each of the thermal zones has all of its faces. The faces have geometry and boundary conditions and properties and windows that are hosted in the faces, and on and on and on, right? So it's just a giant tree of all the information of the building just in a basic text file. Again, no magic here. It's just a text description of the building. And it is what's known as a HBJSON file. So I'm calling it a text file, but if you're familiar, it does not have a .txt extension, has an HBJSON extension. That's just a special format, a specially formatted type of text file, right? Again, no magic there. JSON is just a specific type of format that means you have these curly braces and some commas and blah, blah, blah. It's just a way of nesting things. And HB refers to honeybee. So this is just a special format of text file. That's all this is. And I could come in here and I could change this to yet another. I could actually overwrite the text file. If I wanted to, I could do this whole thing by just typing it in one piece at a time. I'm not going to, but we certainly could. So that's our text file. So that text file was created by this component right here. So this creates the text file. Now the new honeybee element here is that we take that text file, and you can see here that the connection is being passed. We have the text file. The text file gets passed over to this component, and this component creates the Woofy file. So let's take a look at that Woofy file. So we also have this Woofy file. Now this is just another text file of the same building. So the same building with all the same data, but represented in a different format. And I know it might look a little scary. There's like all these like angly brackets and things, but again, it's just a text file in a specific format. All the data is in here. So for instance, we could come in here and we could take a look at our different HVAC systems, for instance, right? So we have HVAC systems. Here's our HVAC system, and we have a bunch of devices. what do we have here? This looks like this is a heat pump system, right? So we can kind of, once you learn the code, once you learn the kind of language, you can read this. You're just reading it, right? This is a system used for heating? Yes. So this must be a special type of heat pump system. Right? So this is just, again, a text description of the building. The important thing about this special format, though, the reason why we created this special text format was because we can open this text file in Woofy Passive, get our building into Woofy Passive. So let me close this. And I'm going to open up Woofy Passive, go over here, and I will go, say, I'm just on my other screen right now, opening up Woofy Passive. So give me 1 second, and this will boot up. There we go. So I've got my Woofy Passive model now. So I've got another piece of software, Woofy Passive, but this is the calculator. This is the tool we're going to use to actually execute our annual energy evaluation. This would be the same if it was PHPP, right? It'd be another application. So I can come over here and I can say File, Open. And if I go to my desktop, you'll notice that my text files don't show up. Right? I exported these things from Grasshopper, but they're not showing up here. They don't, where are they? So all you need to do is come down here, and instead of looking for Woofy Passive project files, you want to just look for XML files. And now all of a sudden, here's my XML file. And all I need to do is grab this guy, say Open, give it a second, and boom, there is our model. Right? So our model has now been translated from Rhino into Woofy. And now with our Woofy model, we can go off and execute our annual energy or certification assessment calculations. And all the data has flown through. So we have all of our different thermal zones, we have our shading elements, we have our HVAC systems, and the like. All of that has sort of come through here into our model. All of this data is defined here in the Grasshopper model. Did that process make any sense, or did I hopelessly confuse everyone? Would you like me to go over that one more time? Would that be helpful? Or does that sort of make sense? Okay, so what do we do with this now, right? So we've gotten our data from Rhino and Grasshopper. So Rhino Grasshopper, we built our model, then we pushed it out to Woofy Passive. Why did I do that? What am I going to do with this model now? Well, I'm going to come in here, shift over to Passive House Verification. I'm going to recalculate my shading real quickly, and then I'm going to take a look at my answers, my results. So now this calculator is taking our model and it's calculating heating energy demand, cooling energy demand, peak heat load, peak cooling load, source energy, site energy, and giving us a bunch of results down here. So we can see that currently as designed, our building is at 36 kBtu per square foot per year. For heating energy demand, 7.25 kBtu per square foot per year of cooling demand, 15 BTUs per hour square foot for heating load, and 3.5 BTUs per hour square foot for cooling load. Notice also that over here on the right, we're getting some big red X's, right? So one of the useful things about this tool is that about the Passive House framework as an energy modeling framework is that it gives us some thresholds and some targets to shoot for. Right? Anybody who has ever done energy modeling before, or maybe in the early 2000s was doing any energy modeling, all too well the process of producing a model, getting a 12, and then stepping back and thinking, is 12 good? Is 12 bad? Is that high? Is that low? What was my target? One of the nice things about the Passive House framework is that we get these very clear targets to shoot for. So what you can see here is that our heating energy demand, heating load, and cooling load are all over the certification thresholds. Now, you're not always going to be shooting for certification. That's not going to be the goal for every project, but it is a very good baseline to use as a reference. So are we far over or far under those certification targets? So we know, we can see right here, or let me do this actually. I'll come up here to localization, and you can see here that our annual heating energy demand target for this climate, for this building, for the FIAS core certification would be 8 kBtu per square foot per year, right? So that would be our target. And we are currently at 36. So whether you're shooting for certification or not, that's a pretty easy evaluation to say, oh, geez, we're not doing so great here. whether we get to 8 or not, we probably shouldn't be at 36. So something is not very good about our project here. So now the question becomes, right? So we've set up our model, we built our model, we exported our model, we calculated our model. And now the question is, why are we doing so bad? Why is the performance of this building so bad? There's all sorts of different ways that we might check that. In Woofy Passive, the easiest place to check that when it comes to heating and cooling energy demand is to come up here to your case, come over to your report, and then scroll down until you see these two graphs right here. So these two graphs right here, let me zoom in a little bit so we can see those a little better. So these two graphs right here are showing us the annual heating and cooling energy demand. So on the left here is our heating energy demand, and on the right is our cooling energy demand. We've got two bar graphs. The blue are losses, heat losses over the period, and the red are the heat gains over the period. The rule for energy balance modeling like this is that the losses always have to equal the gains. So given that the losses always have to equal the gains, or maybe we would say that the other way around, the gains have to equal the losses, you can see here that we have a lot of losses associated with the walls, a lot of losses associated with the roof, not as much losses associated with the ground, a good amount associated with the windows, a good amount with the ventilation, and then not very much gain as a method of balancing out those losses. What that means is that because the gains have to equal the losses, we have to make up for the shortfall with a lot of heating energy right here. So when it comes to our overall heating and cooling energy demand performance improvements, the game here is to shrink that heating, or on the left here, on the right here, this cooling portion, to the smallest amount possible. So, okay, we have a whole bunch of losses, we have some gains, and then we have our heating energy. So how could we reduce the heating energy? Well, there's really only two ways. We could either hold the losses constant and increase the gains. Maybe we would fill the building up with thousands and thousands and thousands of cats. Each cat would emit about 50 watts of heating energy, and that would help to heat our building. That would offset some of the losses. It's probably not a super efficient or effective way of reducing the heating demand in the building. The other method, probably the more effective method, would be to focus on reducing the losses and holding the gains constant. So we really only have two methods. We can work on improving or reducing the losses, or we can work on increasing the gains. Now that's your decision to make as a designer. You get to decide what the specific balance of elements there is, but certainly within our projects, I can say with 100% certainty that we focus almost all of our effort on reducing gains. And I'm very, very skeptical of projects that seek to reducing losses. And I'm skeptical of projects that seek to increase gains. Right? Thanks. Good, Caleb. Yeah, hopefully that makes sense, right? Hopefully that is a little, hopefully that kind of gels a little bit. But let's take a look. Let's take a look at some improvements that we might make. So let's say that I want to attack these losses. So I want to reduce these losses somehow. So how do I do that? What am I going to focus on first? Let's go through it sort of one piece at a time. Should we first focus on ventilation, windows, walls, roof, or ground? Well, of these components here, the walls seem to be the biggest. So I'm just going to say, let's start with the walls. We can start with ventilation. We can start with windows. It's up to you. But I'm going to say, let's start by looking at the walls. And why do the walls have such a high rate of heat loss? Why are they responsible for so much heat loss? Well, probably because they have a very bad R value. But let's check that. So if I click on the wall here, and I come up here to assembly, I have an R12 wall. R12 wall is better than a lot of those terrible glassy condo buildings, but for a single family home in a New York state climate, an R12 is not very good. It is not code compliant, and it is not very good, and it is certainly not a passive house level of performance, right? So I would suggest that one of the very first optimizations and improvements we could make to our building here would be to improve the R value of the walls. So I'm going to say let's start there. Again, we could start in all sorts of places, but there's but I'm going to say let's start with the walls. So what I'm going to do now is go back. I'm going to put this calculator away. We've now done some calculation. We've kind of stepped back and we've looked at this and we've made an evaluation. I'm going to put the calculator away and I'm going to go back to my Rhino tool. Right. So I'm going to go back to my Rhino tool. So I'm going to put this off to the side and come back to Rhino. So what I'd like to do in my Rhino model now is change the R value of every single one of these walls. Now we can also see the R value of the walls here in Rhino. So how can I do that? I'm going to come in here and I'm going to use some Honeybee tools again to see the R values of the walls. So I'm going to come up here to Honeybee and I'm going to come, remember Honeybee is responsible for visualizations. So I'm going to come into Honeybee and I'm going to say visualize, and I'm going to ask Honeybee, please label each of the spaces, or excuse me, please label each of the faces. So I'm going to come in here, I'm going to say label the faces. Now, what do we want to label? I'm going to grab this guy here and I'm going to pass this to this component. So this component is now busy labeling each of the faces. Well, that's a stupid label. That's not a helpful label. What is this label? This is just the unique identifier for that face. That's not what we want. What I want to see is the R value for this face. So I can do that by telling this component to use a different attribute. So I can say, no, don't show me the unique identifier. I don't care about that. Show me the R value. So the way I do that is I come up here to my Honeybee energy. I come across to my energy properties, and you can see here that we have a component called face energy attributes, face energy properties. So I can grab that, drop that onto the canvas, and this will allow me to select from all these different face properties. So I have all these different face properties here, and we can choose any of these. For instance, we could choose the construction U factor and pass that in. And there's our U factor for each of these. Now, unfortunately, this is all in metric. One of the things to keep in mind is that because Honeybee is dedicated to Energy Plus modeling, 99% of the inputs are all in metric. Energy Plus obviously works in metric. And so, this is going to give you metric values. Now, we could convert these over, of course, to our typical American values, but by default, it's going to be showing us these metric values. So this is one way to see the data. But if you're not used to metric values, this data might not be super useful. But for those of you who are familiar with metric U values, you know that 0.4 is a terrible number, right? That's a very high U value for a passive house wall. All right, so we want to change that. So I'm gonna delete that, get that out of there. Again, I was just visualizing. I was just taking a look at the tools there, so I can get rid of that. Now, the way that we're gonna assign our different R value is by assigning a new construction to the assembly. So we have to go through and we have to say each wall gets a different construction. Now we can do that on a face by face basis, or we can do that to the entire model all at once. So let's do it to the whole model all at once, and we can kind of look at how we might dive in and do individual faces as a second order. So the way that we do that in Honeybee is by coming up here to basic properties and using what are known as construction sets. So construction sets is the language, that's the sort of vocabulary term that Honeybee uses for managing assemblies, the wall, the roof, the floor, the ceiling, what have you. So if I grab this construction set and drop this onto the canvas here, you'll notice that I have this new component, which is creating a construction set. So we have an energy construction set, and it takes in as input an exterior construction set, a ground construction set, a subface construction set, and we'll talk about what all those are. So this is actually asking us for more inputs. All right, so first of all, we want to look at the exterior wall. So I'm going to build out what's known as an exterior subset. So I'm going to come back up here to basic properties, and I'm going to come down here to exterior construction set, drop that onto the canvas, and now this exterior set is going to feed in to this exterior set. So now we finally have the ability to set the actual exterior wall. So now we can build up the actual wall and pass that over to this construction set. The construction set will then be passed over to the zone builder, and those constructions will ripple through, right? So we're kind of coming back to the earliest part of our definition, making some modifications, and to the questions that were asked, that Kevin was asking earlier, that data then ripples through all the way through the definition. And then when we re-export, we're going to update everything there. Oh, so Clark has a good question there. Where did R12 even come from? Because it's a great question. Because we never told Honeybee what to do, it applied a bunch of default values. And specifically, it uses defaults for, I think, Zone 4 commercial office. I believe that's its sort of default assumption. And so if you don't tell it what to do, it's just gonna apply commercial office style interior program and exterior envelope elements. So here we're going to override that. We're going to say, no, we're not making some shitty glass office building. We're making a passive house building. And so we're going to give it actual good R values for our walls here. But we haven't yet. All we've done is set up the infrastructure. Now I need to actually build this exterior wall. And we can do that in lots of different ways. Probably the standard way is using the Honeybee tools. And so I'll show you those, and then I will show you an easier way to do it, because the Honeybee tools are actually a bit laborious. But let's look at the Honeybee method first. So I might come up here to constructions, and if I want to build a new wall construction, I would use this component right here called opaque construction. So I drop this onto the canvas, and this construction is asking for a list of materials and then a name. So I might call this Ed's Wall Assembly. Say Ed's Wall Assembly. And once this construction gets created, I'm going to pass this construction to my external wall there. Right? You notice right now it's glowing yellow, it's unhappy, and it's giving me a warning. It says, hey man, you didn't give me any materials. Like, I can't build the construction out of nothing. So what am I going to build this assembly out of? Well, first I need to make some materials. So I would come up here and I would make a material. So I'm going to make a new material, and here's where we would start to build up our assembly. So I might say, oh, the outer surface is going to be plywood. So I would say plywood, and maybe it's a ½ an inch. So what's that, 0.17 or 17 millimeters? Again, everything here is in metric, unfortunately. I'll talk about some options for working in US units in a second. Conductivity is going to be like 0.1, 0.13, something like that for, plywood, right? And then we have to put in some inputs here for density, specific heat, and roughness. I don't care about any of that for passive house modeling. So now if we were doing energy plus modeling, this would matter, but I don't care about these values at all for passive house. So I'm just going to put in 999. If we were doing energy plus modeling, doing hourly modeling, dynamic modeling, where we take into account the effects of heat storage in the materials, those data points would be important. For passive house models, those are not considered. And so we can just put in a generic element there. So I can then pass this material off to my construction, and my construction is now made of a single layer of plywood. So my walls are now a single layer of plywood. Well, that's not very good. We probably want more than that. So let's add some insulation. So I'm going to come back up here to constructions. I'm going to come and say opaque material. And here I'll call this, we'll call this insulation, or maybe we'll call it cellulose insulation. And let's see, we need to give it an R value, a total effective R value. So let's say that we want a total U value of 0.1. And so let's just do the math real quick. We'll say 1 over. And so I'm just using a little calculator component, so you can see how we kind of grab different components and put them together in order to execute the calculations. And we'll say that's our R value. Here we go. And now what we need to do is pass this guy along with it. So we've now got two materials flowing in. So we've got two different materials. We've got an insulation layer and we've got a plywood layer. So we use a couple different components there. This one here asked us to specify all sorts of elements, asked us to put conductivity and thickness. This one's asking us just to put the R value. So different components that we might use in all sorts of different ways. I'm going to show you an easier way to do this, I promise. But this is maybe the standard honeybee way. So now that we've set all this information, what I would do is I would come back over here and I would re-export to Woofy Passive. So I would rewrite this to put Woofy Passive. Then I would come back to Woofy Passive. I'd say open. I would go to my desktop again. I would choose my new file, say open. And now what we'll see is that notice our heating demand has dropped to 22.9, right? We were at 36 before. So if I come in here and I take a look, now all of a sudden I've got an R60 wall assembly. And yes, we're sort of switching back and forth between metric and IPU values, which is very difficult. Again, all of the honeybee tools, the basic honeybee tools are all written using SI units only. So I'm going to show you guys both an easier way to do this and a way that can accommodate United States typical IP units. So I'm going to show you both of those right now. But just as a basic workflow, right? If I go back here for a sec, notice here I've got Ed's wall assembly. And if I wanted, I can actually go in and see the different layers. If I go and I actually take a look at the assembly, here's our assembly here, sorry. Notice I've got my plywood layer, my cellulose insulation layer, and whoops, oh boy. There we go. And there's my assembly. I've got my plywood layer on the outside, my insulation layer, and then obviously I could build it out with gypsum layers and this and that and the other, right? But I've got all my data is flowing through from the Rhino model into this calculator, and then I'm getting an updated heating energy demand calculation right there. We can also go back to our case level, take a look at our summary report, and notice here that our walls, remember our wall heat loss used to be quite large, but now notice that it has shrunk to a much, much smaller level. So we've held our gains constant and we're reducing our losses, and that is improving our heating energy demand. Andreas has a question: if you use PHPP IP, does the IP units flow back to Honeybee? If you use PHPP IP, it will automatically convert everything over to IP units. So if you're using the IP version of PHPP, everything should automatically flow through in the units that you would expect. So no matter how you model them here, when it converts and gets passed over to PHPP, it'll convert everything over. So this is pretty nasty, right? This is kind of big and unwieldy, and we're being asked to input some data that we don't really care about, and everything's in SI units, which I like, but not everybody does. Certainly, if you're working in the United States, you might not be familiar with those kind of units. So I'm going to say that this is not the way that we want to do this. I'm going to get rid of that. I'm going to say, we're going to use a different tool to build up our exterior wall instead. The important thing here, right, is this is a tool kit. It's a kit of all sorts of tools. You get to put them together in whatever manner you think works best for your process and your workflow. So I'm going to come in here because I don't want to build those big assemblies with lots of things. I'm going to come in here to this Honeybee PH, and I'm going to grab this schematic design assembly builder. So this is going to allow me to define my assembly very, very quickly using just a few data inputs, and I can work in IP units. I'm going to grab this component, drop them onto the canvas. So this is an alternative assembly calculator. So I'm going to give this a name. I'm going to call this Ed's other wall assembly. So that'll be the name of our new construction. And notice here that it's asking for a U value, just like we were asking for before, but this component is smarter. So this component can accept an input of something like 40 R value in IP units. And if I pass that in, this component will convert that over into our SI units. So it's going to build up a whole construction of many different layers, and it's going to assign the R value of 40 to that wall assembly. So now all I need to do is pass this through to my wall, come over here, rewrite to Woofy passive, bring Woofy passive back, say open, go to my desktop, find the new version. And now if I click on this wall, notice it has an R value of 40. So this honeybee component, this honeybee pH component, allows us to work much, much faster. Now, we don't get the ability to define, oh, there's a layer of plywood and a layer of this and a layer of that and a layer of the other. But if we're at the schematic design phase and we're just testing out to find the limits, should it be R40 or should it be R60? Should it be R20? We can use these schematic design components to very, very quickly build up our pieces here. And again, we can work in IP units the way that we might be more familiar with. Right? So we have these alternative calculators here. I'll just clean up a little bit. These alternative calculators here that we can use to set our various assemblies. So that assembly gets created. The assembly becomes part of the construction set. The construction set is used and applied to all of the geometry, and then that flows through into our Woofy model there. So again, lots of different ways that we can do this kind of stuff. So Alex, I see you have a couple questions there. Could you build actual wall assemblies in Honeybee? Yeah. So right. So we've got those there. And then how do you account for framing? Great question. So we have another calculator, another component up here, which allows you to build these mixed materials, same way that we might do in PHPP or Woofy passive, where you can say, oh, I've got a base layer of insulation, and then I've got a stud, and the stud represents, 7% of the total assembly layer. This becomes a material layer, which can then become part of the total assembly there. So there's this little sort of stud element there. So you can do studs. That only works for wood studs. You would not be allowed to do steel studs using that method, but that's a ISO rule, right? So you're not allowed to mix steel studs into your assembly layer there. But you can certainly use it for wood studs if you wanted to. Okay, so
could you can you use an external calculator, say like the R value tab of PHPP, and maybe have a PHPP that's containing all of your inputs and somehow funnel them into the Rhino/Honeybee or Grasshopper Honeybee interface?
That's a great question. Great question. So we actually use a whole different process where we use what's known as a database. So we have an online database of all of the material data for our projects. We have all of the materials get combined or put together into actual material layers. And then the assemblies are actually built of multiple material layers within this database. This database can be connected directly to the Grasshopper model, and you can automatically build up all of these assemblies within the Grasshopper tools. So this database is directly connected to the Grasshopper tool. Now, I'm showing you guys today the sort of point and click style of modeling where you build everything in Grasshopper. In an actual project, like a large project with lots of input data, the better method is to actually offload the inputs to something like a database. We like to use Airtable, but there's all sorts of different ways you do it, and then have that data flow into the Grasshopper model and then build up everything automatically. We do that, as you can see here, all of the input data for, well, in this case, assemblies, but also windows, appliances, room level data with flow rates per room level. All of this is managed in a database, and then that flows in. So we find that to be much more effective in terms of actually modeling. And that's kind of like a whole other version or method of modeling. So 100% yes. And I think that's a much better way to do it, especially for big projects. We're sort of showing a more exploratory kind of point and click style right here. And the tooling supports both of those. You'll notice over here that there are some components that allow us to, go and download that data from those web-based databases. So there's tooling in here if you want to use the Airtable thing specifically, where you can like download the table of data and then unspool it and automatically create assemblies and windows and whatever else. So all of that is also baked in. So great question. You could also, of course, use local CSV files. So you could, for instance, you could say, oh, I want to point this at a local CSV file. You could find a CSV file somewhere on your, somewhere on your computer, or an Excel file, and you can pull that data into Rhino or Grasshopper and then use that to build up so it doesn't have to be a remote database in the cloud somewhere. It could be a local CSV file. In any event, all of that can flow in and be used to build up these various components. So yeah, very flexible in that regard. It allows all sorts of different ways of working depending on the type of project that you're up to. One of the main reasons why we think that Rhino is a better information management tool than SketchUp is because of that sort of capability, the way that I can pull in data from somewhere else and use it to build up all of these elements. So I can explicitly connect this platform to other data sources. So for our purposes here, though, let's carry on with our optimization work. So we were saying, oh, we got down to like 22 or 25 kBTU per square foot per year. That's pretty good. But we have some other assemblies that we should probably set. So maybe we should set our exterior wall in this case. So let's do this. I'm going to come up here and I'm going to grab another one of these SD components. I'm going to drop it onto the canvas. I'm going to call this Ed's Good Ceiling Assembly. So we'll do that. And then what should we give it for an R value? You want to say like, I don't know, like 60, say like a 60, an R60 in IP units. And then we'll pass that in there. And then we can take this construction, which is my new ceiling, and I'll pass that to the roof. That becomes part of the construction set, gets applied to the geometry. So now when I come over here and I export, and I'll come back to my Wi-Fi passive. Where's my Wi-Fi passive? Here it is. Come back to Wi-Fi passive. Say open. Go back to my desktop. And there we go. So now we're down to 19, right? So we've done much, much better. We're doing much, much better. So we've got let's just double check. We've got a R40 wall assembly. And then if I go to the ceiling here, we've got Ed's Really Good Ceiling Assembly at R60. So we've now updated the R values very, very quickly on our project here. And we could go in and we could do the floor as well, etc. So we're doing better, 19. Remember, our target here was 8. So we're still not doing great. We're still, 200% of our target. So what else could we do here? Well, let's go back to our case and come up to passive house verification. And I'm going to scroll down till we see our graph again there. And I'll make that a little bigger so that we can see it. So, okay, so we've done, so again, we're looking at this graph on the left here. So we've done a pretty good job on our walls, right? We've beaten the heat loss of the walls down. Notice our ceiling heat loss is now so small that there's not even a place to label it ceiling. So that's this little bar right here. So we've driven the ceiling heat loss way down. The ground heat loss, the ground floor is high. We could probably do a better job than that, but it's not the worst offender, right? The worst offender here in terms of the next most logical optimization would be, I would suggest, to reduce the heat loss of the windows or reduce the heat loss of the ventilation system. Let's take a look at ventilation system first, and then we'll talk windows and shading last. So, okay, so the ventilation system here is responsible for a lot of our overall heat loss. Why is that the case? So let's take a look at the ventilation system quickly. So come down here to ventilation rooms. So first things first. So we have a ventilation schedule here, so that's fine. We can adjust that if we wanted to. We can set that in the Rhino model, but I'm fine using the default schedule. If I come over here to my room ventilation, I have floor 1 and floor 2. They're using the default schedule. They've got some default air flows associated. Now, we didn't set any of this, right? To Clark's point, where is this data coming from? These are default office flow rates. So we might want to go in and change these to be, residential flow rates. That's fine. We can absolutely do that. But if you look at our average air change rate, it's at 0.4. So maybe for schematic, we might say, well, you know what, it's close. I mean, yeah, maybe we want to be 0.5 or maybe down to 0.4, but 0.44 is not that far off. So I don't actually think that the reason that we are seeing such high losses through our ventilation system is because of flow rates, right? The flow rates are actually not that far off. Yeah, if anything, they're maybe a little low, right, for a building like this. So why are the losses so high then? Well, the losses are so high because if we come down here to our systems, so here's our mechanical systems, and we take a look at our ventilator, currently our heat recovery is set to 0%. So we have 0.44 air changes per hour. We have a lot of air flowing through the building, which is great for overall health, but it's a 0% heat recovery, which is terrible for energy efficiency and comfort. So obviously we should change that to be a passive house style ventilation system. So we've got our passive house ventilator. It is connected. It is working. It just has a 0% heat recovery. So how do we set that now? So let me put this off to the side and bring back my grasshopper model. So I've got my building here. So where are we going to set the ventilation flow rate? So the ventilation flow rate is going to be over here. Yep, Caleb says, let's try 75%. And I think that's a great idea. So up here we have our mechanical ventilator. We could give it a name too. We could call this Ed's Good Ventilator, or maybe we call it HRV, right? Use the sort of standard terminology there. So this is my ERV, and it's not going to be 0%. Caleb says, let's try 75. So I agree. Let's try 75% heat recovery, just as a first order, right? Again, we're kind of testing out the boundaries here, trying to find where the limits are and what we kind of need in order to get this working. So I'm going to re-export to Woofy Passive, and I'm going to come back over here, and I will say update. No, I don't need to save that. Why is this in the way? There we go. Sorry. Open, go to my desktop. And so now, if I come down here and look at my systems, and I look at my ventilators, so there's Ed's Good HRV, and notice now we are at 75% heat recovery. And if we take a look at our total heat demand, now we're at 12. So getting a lot better to 8. We're getting a lot closer to 8, right? We're doing much better. If I come back up to my case, and I come down and I take a look at my heating energy balance again, now notice, oh, having a little weird artifact thing because of the recording. I apologize, but you can see there, right? So our walls are our wall heat loss is quite low. Ground heat loss is medium. Roof heat loss is low. Ventilation heat loss is now quite a bit lower. And at this point, the biggest source of heat loss are those windows. So we've done a really good job of beating back the heat loss through almost everything. And we're at 12.5 kB2 per square foot for heating demand. We're supposed to be at 8. So can we get all the way there by improving the window performance, right? That's the question that we want to pose next, is what can we do to improve the window performance? Well, let's take a look at the windows here in Woofy, and then we can take a look at them in our Rhino model. So generic double pane with a 0.3 U value. So not very good. Code compliant at least, but not very good for a cold climate. So we would definitely want to improve that U value as a first order optimization, right? We would say we can get way better glass than this. So let's take a look at how we would improve the performance by changing the glazing. So come back to my Rhino PHPP here. And the way that we're going to do this is by coming back here to the beginning, and we're going to make a new construction for the glass. So same way we made a new construction for the walls and the roof, we're going to make a new construction for the glass. Now we're not going to use these components. These components here build opaque assemblies. Instead, we want to build a transparent assembly. So we have a bunch of different tools up here to do that. So we can create our passive house windows by using this guy right here. So this will allow us to build passive house window constructions. And the passive house window constructions can then be passed to a subface construction set. So let's set that up. I'm going to come back up here to, Honeybee Energy. Come over to basic properties. And I'm going to use this subface construction set and I'm going to pass this window construction to my glass doors, my fixed and operable windows. Right? So I'm going to pass the same construction to all those, and then this construction set will become the subspace construction set, get applied to all the windows in the project. But what is, we haven't built the window yet. So let's build up this window. Now this is a passive house style window. So this expects a frame and some glazing. So you can see here that we have inputs for frame and glazing. I'm going to come back over to my Honeybee PH, and let's put the glazing in first. So I can put in my passive house glazing, and I'll plug that guy in. Now we should give this a performance value. So just like before, because this is a Honeybee PH tool, we can put in either SI or IP units. So I could say 0.09 U value in IP. And we'll put that in there. This will do the automatic conversion over to SI units. And we'll call this Ed's Really Good Glass. Give it a name just so that we keep track of it. Oops. There we go. So there's our glass. We're just going to try 0.09. See, we could try some different values there. And then the other thing we need to do, of course, is make a frame. So I'm going to come up here and grab some of these frame elements. So I'm going to build a frame element, and I'm going to combine the frame element together into a frame. And then this frame is going to pass in there. So the frame element will come in here, and I'm going to use the same frame element for all. And now we just need to input some values for the frame element. So let's give it a U value. Let's say that it's like 0.2 U value IP, right? The frames are always worse than the glass. So we'll say 0.2, it could be better than that, but something like that. And maybe it's 4 inches in width. So we'll put in 4 inches there. And then I'm just going to leave the rest of this stuff at the default. I mean, we could fill it in, but I'm not going to worry too much about it for now. So, and then we should give this a name. We'll call this Ed's Good Frame. There, and then we should give our construction a name. We'll call this Ed's Window Construction. So we'll give that'll be the name of our window construction there. So we build the frame, or excuse me, we build the frame element, the frame elements. So we can have up to 4 different elements. If I wanted, I could make a different element for the sill. Why don't I do that real quick? We'll call this sill frame, and maybe it's 6 inches for the sill, and maybe the U value is a little bit worse because it's the frame. And so maybe I want to use that one for the bottom, and then I want to use Ed's Good Frame for the other sides, right? So I might have a mix. I could mix and match the frame elements. They get combined into a frame type. The frame type gets combined with glass into a construction type. The construction type becomes part of the construction set, which gets passed to the geometry. So now this has been applied to all of the windows in our project. So now if we come over here, and we rewrite this to Woofy, the next time I open up Woofy, you should see all the new glass in there. So come over here, come to my desktop. And now if I click on this guy here, you'll see I've got Ed's window construction with a U value of 0.16. Right? So much better glass. Much better performance. We are currently at 9.2, but I should note that we should recalculate our shading. We haven't recalculated that in a little while, so we're at 9.6. All right, so we're still at 9.6 kBTU per square foot for heating energy demand, and so we would then have to figure out what our next optimization would be here, right? whatever the next thing that we might want to do to our building to improve performance. So again, we might come up here and come down here and say, well, of these things, which of them could further be optimized? Probably the thing that jumps out at me right now are the heat losses through that ground surface. So maybe the last thing that we should do would be to update our ground floor surface, right? We never set the assembly for that. So maybe we go back to Rhino and we update the assembly for that in order to get us down below our 8 kBTU per square foot per year heating energy demand target there. So that's the basic process for how the workflow goes there, right? It's a bunch of back and forth during this design phase in order to use Woofy to perform the calculation, or PHPP to perform the calculation, and then you go back to the Rhino model and set and update those things. Oh, sure. So Clark says, could we show Sure, I'd be happy to show the database. It's a great question, Clark. Let me actually, I have time. I will show you guys that. What I'd like to do for the whole group, though, is actually show a little bit of the shading stuff real quickly, and then let's talk database stuff, because I can open up I'll open up a big project and show you how like an actual project is configured. We can kind of take a look at that. But if folks have to leave at 12, I would like to just show the shading real quick, and then we'll show the database stuff. It's a great question. So let's talk shading for just a moment. Christina brought it up. It's a great question, and it's one that comes up all the time. So shading. So shading calculations in Woofy are going to be done internally in Woofy. So you can see that we are pulling in some shading geometry that gets passed to the model, and then the entire thing gets exported. Shading calculations are done in Woofy. PHPP is very different. And then we've got another method of shading that we want to just demonstrate here, which is going to be more helpful in the design phase. So there's all sorts of different kind of permutations to shading, but I want to especially show the design phase shading optimization here. So let's start with that. I'm gonna turn this off for a second, and I'm gonna come up here to shading. And I'm going to grab a couple of different tools. So I'm going to come in here and I'm going to use this component right here, which is going to take our honeybee rooms, and it's going to build up the geometry with the window insets for all the different windows. So this guy here is going to build up all of these. And so this tool is going to be helpful in that regard. So it's going to automatically create the window inset, which can partly shade the building there. So that's what this component is going to do. This is then going to be used and passed off to a calculator. So this is different than the way we've done a bunch of other stuff here, right? For the most part, this toolkit is not calculating anything. This toolkit is merely passing off data to somebody else's calculator, PHPP, Woofy Passive. This calculator is going to do a bunch of work inside of Rhino Grasshopper. So let me pull it up here so it's a little more isolated. So let's do this. I'm going to give this a trigger. So when I set this to true, this is going to run. But if I set it to true right now, nothing's going to happen. So we need to give it some information. So first of all, we need to give it some shading surfaces. So I'm going to give it these shading surfaces for both winter and summer. We can come back and talk about how you might add trees for one and not for the other. And the other thing we need to do is give this some climate data, give this some climate information. So I'm going to grab this settings component here, click settings into settings. And now what I need to do is input an EPW file. So we're going to do a very, very detailed shading assessment here, much more detailed than Woofy or PHPP. And to do that, we need an EPW hourly climate model file. Now, where do we get an EPW file? Well, we can come over here. We can say EPW map. It's all free, open source. So you can come in here, go to EPW map or Ladybug Tools/EPW map, and we can come in here and we can grab any EPW file that we want. I'm going to grab New York City JFK. I'm here in New York City. I'm going to say copy, and then I'm going to come back here and I'm going to paste what I just copied here into a component. So what did I just copy? Well, I copied an address. Notice it's a website, https/blah blah 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 blah, and it's a climate data file. So how does this climate data file go over here? If I just connect it, it doesn't work. It's broken. So how do I actually download this climate file? To do that, I'm going to come up here to Ladybug, and it has a tool here for downloading weather files from the internet. It's going to grab that. It's going to create the EPW or unspool and unzip the EPW file, which we can then pass off to our calculator here. So this guy is now downloaded from the internet for free, right? All the data is available there for free, and we can use it to execute our simulations now. Now, there's one other thing we want to do here before we go off and do our simulations. We want to give it a grid size. So we want to give this a grid size. And I think what we want to do is give this a grid size of like 12. Our units are inches. So for now, let's say 12 inches on center. I think that'll give us a decent grid. We can try it, and then we can update that if we need to. So now we've got our settings, our EPW file, our grid size. There's a bunch of other stuff we could set, but we don't need to. And I'm going to say, go ahead and calculate. And hopefully this runs quite quickly. So this calculated, but what happened? What did we see here? I'm going to put a preview component onto the canvas here. And notice now we're seeing a bunch of information. So let me do this as well, just so that we can see this clearly. Do this. It's just so we can kind of see what we've got here. So now what we're looking at, and I can preview the legend here as well, so that we see our values. So what we're seeing is radiation. What we're seeing is solar radiation on the various windows. Whoops. Sorry, using the wrong component here. Geometry. There we go. So now we can see the actual kilowatt hours of radiation on the various windows. Now this is a pretty coarse grid, so we might want to set this lower. So let's maybe set this to 6 inches on center and see if we get some slightly more nuanced results here. It'll take a little bit longer to execute the calculation, but there we go. And we could maybe even set this smaller. Let's maybe set it to 2 inches on center and see if that kind of gives us even a little more nuance there. So it's going to definitely increases the calculation time significantly when we do that. But here, what we're able to do is really see. Oops, I might have drastically increased the calculation time there. We'll see if it comes back to life in a second, or if I pushed it a little too far. What this will allow us to do, though, is to really more clearly visualize exactly how and where the solar irradiation is affecting our building, right? So we can immediately see that those south-facing windows are much more are seeing much more solar irradiation than the east-west or north-facing windows there. And we can also do things like this. We could say, well, currently it's only taking into account the self-shading from the windows. So maybe we want to actually add a little bit more. So let me just show it very, very quickly. I might come over here and I might say shading. So I'm making a new Rhino layer, and then I might use a pipeline here to pull in any shading geometry. And maybe what I'll do is come in here and I will say, I'm going to build a little shade surface. And I'm just going to roughly position it as a horizontal shade over the windows there, just to see if we get some effect. And then what we'll do is we will pull this together. So I'm going to merge together this and this. Don't worry too much about what I'm doing right now. I'm just showing it quickly so that you can kind of see the effect. Do that. And we'll let it calculate for a second and see if that. Right. So now what we've done is we've added a new shade, and you can see exactly how and where this shade is affecting these windows, but not affecting these windows over here. Right. So what we might say is, oh, I actually want to grab this and I want to extend it out this far because I really do want it to shade those 2 windows on the side over there as well. And now you can see that it's starting to affect those guys there. So we can use this type of visualization and calculator internally to improve the performance of our building very, very quickly, right? So we can see very, very quickly how and where the solar shading is impacting these things, which is great, right? And I can see immediately that, oh, these guys down here aren't shaded at all. So I actually ought to put a second shade, down here. To help shade those guys down at the bottom there, and you can see there now I'm getting better performance on both of those, right? So I can use these tools to very, very quickly improve my overall shading situation. This would then flow into our WFI or our PHPP calculations, but these types of tools internally to the Honeybee PH toolkit allow us to do a lot better improvement of the actual design, right? So Christina asked a question there. Could you use this to set a certain amount of translucency for trees? Yes. So right here, what we're showing is just a very simple, very fast calculator. The Honeybee Radiance calculator tool has all sorts of all sorts of interesting inputs. Where would we be? Especially for things like translucency. So you might be able to, you can apply not only, here we go, translucency modifier. So not only can you affect like the schedule, you can say like, oh, these shading objects exist at this time of day or at these seasons. And then we can also input all sorts of other information here around opacity and translucency for the radiance simulation, which will give you an even more accurate and nuanced calculation for these types of shading factors there. So yes, there's all, you can kind of take this as far as you want in terms of, level of complexity and sort of bits and pieces there. Nadia has a point there about shutters and drapery. Good point. A great point. So if you come over here, you'll notice that there's actually a tool here for doing passive house style interior blinds. So these blinds can actually, this blind material can actually be added to a window so that you can then simulate the effect of internal blinds. And then Honeybee has all sorts of tools for doing like time-based blinds as well. So again, there's like a ton of complexity and nuance that you can build in if you want to, right? There's like it's a toolkit, right? So there's all these different tools. You can deploy them if you want to, and if you are interested in the results, in the impact of those things. So yeah, those are it's a great point, Nadia. Those could make a huge impact, especially on bigger buildings. External shades are not going to be realistic. And so in those cases, maybe something like internal blinds is exactly what you're going to be used there. Caleb has a question there about setting the window back set. So you would do that over here using this tool right here. So there's a component here for setting the window install depth. And so you would take in these apertures and then you would set the window depth. You can either set one number for all of them, or you can pass it a list of numbers and it'll set the window back set for each one uniquely. So there's a little component here that allows you to modify that install depth, which can make quite a big effect. So if I set this to 12 inches, if I set the window install depth to 12 inches, and then pass this along, that's going to affect our shading calculation here quite significantly. Or I think it will. Because it pushed them all quite a ways back. So it's a little hard to tell here, but it affected that because it moved them back in space there. So the whirlwind tour through the different bits and pieces here. Those are kind of some of the main bits. Obviously, there's a ton of stuff here that we didn't have time to cover. I mean, there's a ton of mechanical stuff. There's the whole universe of hot water. There's a ton to say around spaces, as well as occupancy and renewable energy and programs, climate. There's a ton of other bits and pieces here, but hopefully the basic workflow, it makes sense, right? Building up the model, changing and editing the model, and then pushing that data out to either PHPP or Woofy Passive. That's the sort of general workflow there. So questions on any of that? If there are, maybe what I'll do is close this and I will open up another project so that we can see what a more complicated project would look like. I could share one of those with you guys while we're, if there are any questions.
So Ed, you would explain that input probably at another, so we at 12 o'clock, you guys can of course hop off. You want to do 50 minutes or what's your?
Yeah, I mean, it'll take me 5 or 10 minutes just to show Clark the database method that he was asking about there, and then anybody who has to, I'll go, of course. But for those who are interested, I'll show you a more complex project here, and we can kind of take a look at how that is put together, and how it works with the database tool.
So Ed, just a general question. I know you have, so you worked out the two-way data flow for the PHPP. Are you planning to try to do that for Woofy Passive, or is there some kind of infrastructural impediment to that?
So Woofy Passive, and we've spoken with the developers of Woofy Passive. Woofy Passive will not allow us to do that type of direct read and write from the application. It's just the way that they have built that tool does not allow for that type of manipulation, which is why we have to use this kind of clunky method of creating the XML and then opening the XML. So we can't actually work directly with the WFI application, which means we cannot read data from it, unfortunately.
Right.
So that has been a hindrance, and that is a great frustration. But it's just the way that they architected that software. It does not allow for that type of work, sadly.
Okay.
Hopefully in the new version, whenever that becomes available, hopefully in the new version, we might have better access to that, but I'm not holding my breath. We'll see.
Right.
We'll see. I see Justin has a question there about PDF export tools. Yeah, there are some PDF printing and export tools as well. When you build up this rich building information model in Rhino here, you don't want to then laboriously by hand transcribe data to a drawing or something. So what we have are some tools to allow you to automatically generate things like floor plans and exterior elevations with automatic tagging of all the information like TFA or ICFA factors or thermal bridges or R values or heat loss factors, that kind of thing. So there's a bunch of those tools which are built in as well. So yeah, those do exist. Those are let's just say those are a work in progress. All of this is a work in progress, right? Like I said, this is not a product. This is a project. This is a thing that we use for our internal processes that I'm happy to share with everyone, but this is not like a piece of software that is being sold. And so, yeah, there are some janky bits. There are some bits that are a little rough around the edges, and PDF tools are definitely one of those, I will readily admit.
Do you know of any problems with importing and exporting information from the various types of BIM software that's out there? Because oftentimes we end up with large projects where people have already modeled their building entirely in BIM, and then it's hard to get the information into Design PH or PHP.
It's incredibly hard. It's a great point. It's incredibly difficult. There are many, many, many problems with it. Fundamentally, the problem that we continue to see is just that the models are built to make drawings, not to be used for analysis. And it's small things and big things. I mean, it's small things like, oh, that wall in Revit that looks like one wall is actually made of two walls that I smushed together because there's like an outer portion and an inner portion. And so you can't actually consider it one wall. And so when you export it, it comes in as two layers that are like overlapping each other. Small things like that. And then big things, just around, where the edges are and what you consider a floor and what's inside and what's outside. There's huge problems. We constantly just rebuild the model. What we have done, we have basically given up on extracting data from Revit models at this point, and we just take flat CAD and bring it into Rhino and build it up ourselves. Now, maybe someday we can stop doing that, and I would love to stop doing that because it's a huge amount of work, but we cannot get the data we need from Revit models because the models they're just not built for us to extract data. They're built to make PDF drawings. That is my interpretation of like where the problem lies. And so, yeah, we cannot make it work, unfortunately, for us.
So if you were working with a design team that involved you from the early schematic times, you could use Rhino to feed information to both BIM and the energy calculations, but you need to do that from the start.
Potentially, even the teams that we've been involved with from the start, though, it has been challenging to get the data that we need encoded or embedded in the model. I mean, even something as simple as room by room ventilation flow rates, even just getting teams to add that much data to the models has proven really challenging. And we haven't had a lot of success, even with teams where we're involved from the earliest stages. And again, fundamentally, I think the issue is that the models are not the deliverable, and that nobody is paid for making a nice model with the right data. They're paid to make a drawing, and the mechanical engineers are paid to have a schedule, and that schedule is made in Excel or AutoCAD or something. And like the data is just not embedded into the model. So until people start getting paid for making nice models, I feel like we're going to continue to have this problem. That's my interpretation of what I've seen. I could be totally wrong on that, but that's what I think is happening fundamentally. So the models are messy.
Benefits of having a good model could last long beyond construction, though. I mean, it could be a tool for operations and maintenance as well.
Oh, it could be huge. It could be huge, right? Absolutely, absolutely. But we're seeing, but we have yet to see, we have yet to see that happen, right? As you say, a rich data model could feed into operational energy calculations, embodied carbon calculations, building takeoffs, phasing, scheduling, material quantities, but they don't, is what we continue to see, is that the models are just not built that way. I have never worked with a big manufacturer or big contractor who has like taken the architectural model and used that. Like even the big companies who use building information models, like build their own in-house, is what we have seen anyway. And so, it's really been a hard thing. And from our perspective, basically what we do is we just build up our own version of the model. Highly inefficient, tons of room for error, not a great idea, but we just are not able to get what we need from those Revit models, unfortunately. So we like for whatever it's worth, we like the flat CAD drawings. We can just take those and build up the model the way that we want it to work. So here, I just want to show very briefly this example of a full project. So this is a much larger project. So this project here is, I think it's 400 units or so. Let me just bring this up. It's I think it's 10 stories, 400 units, Fias project here in New York City. And so this is a much larger project with a lot of data, 400 individual units to track, as well as a lot of non-residential, complex podium, all sorts of complex geometry and elements. So this is an example of like a full model but we're moving through the same sequence. So on the left over here, we're building all the geometry, assigning all the constructions, building all the windows, setting up all the spaces, setting up things like occupancy and non-residential programs, configuring the mechanical system. So mechanicals, ducting, ERVs, hot water systems, exhaust fans, thermal bridges, configuration, solar systems, shading, and then finally exporting out to Woofy at the very end there. So it's the exact same process that we just looked at, just a lot more pieces, a lot more components. And specifically what I wanted to show was that all of these green components are pulling data down from those cloud databases that we're using. So maybe one of the easiest ones to look at would just be like this exhaust, this guy here, these exhaust fans. So we're pulling down a ton of data from our web database there. So you can see here, we've got these Airtable data. We've got all of this information. Where is all this coming from? If I go back to our guy here, we've got our fans. And so you've got, dryer exhaust, makeup exhaust, trash room exhaust. You've got the ID number. You've got the different areas. And then, of course, you've got things like CFM information, voltage, specification, cut sheets. Eventually, we can add those directly to the database here. Then all that data flows through. So for instance, here's like TX2. Go back over here. There's TX2, right, with an energy demand of 1,081 kilowatt hours. Where do we see TX2? I lost my place. Here, TX2, and right here, energy demand 1,000 watts, 1,081 watts. So that data is then flowing through directly into this fan component. And so the fan component is, taking, here we go. So for instance, there's TX2 and where are we? Energy demand here. You can see TX2, 1,081 watts. So that data is flowing from the internet down into the grasshopper model, into a fan, which is then hosted on one of the spaces, and then that flows through into the Woofy model as well, right? So there's no possibility. I mean, there's always possibility, but it's much easier to ensure that the data model or the document model, which is this guy over here, so this is going to be a list of cut sheets and specs and everything, is automatically aligning to the Woofy model, because the Woofy model is built from that database. Right? So that's the sort of way that we would pull those things together. And you can see here we're doing it for exhaust fans, do it for thermal bridges, do that for ERV units. So the same way we can pull down the ERV data, so the ERV unit data. So this project's got whatever 25 ERVs, all of them at different heat recovery values, different specs. So we can pull down all that data, build up 25 ERVs, and then host them and connect them to the different rooms that they're associated with there automatically. So all of that gets done automatically. Back in the beginning, do it for rooms. And then earlier, where are we here? Earlier, we could do the same thing for all the envelope elements. So we can pull down all the material data, all the material layers, all the construction assemblies, like we looked at building those different construction assemblies. And then again, all of that is connected here to the material database, the material layers, and then the actual construction assemblies, which are made of a variety of layers all put together. So again, all of that comes from the database into the building information model here.
Is that coming from a Google sheet or something?
So
or
this is a
online, or is it part of?
Yep.
Woofy
So this
Passive?
is a tool called Airtable. It's a lot like a spreadsheet, but it's actually what's known as a database. So this is a relational database, and it is free. It's free, so it's a free tool, and you can build up these databases and then connect them to your energy model, which has been super helpful for us. So it's called Airtable. That's the name of the service. It's like a, it's a whatever. It's like Google Sheets, except it's a database, not a spreadsheet.
But isn't it? But like, couldn't? Well, I don't know.
You could do it with Google. Yeah, you could
do it with a Google Doc, because I was wondering whether, like, just in terms of the workflow of a project like this, like, and how they manage their schedules, or for bidding and all the rest of that. And so if they want to do substitution, like that substitution would automatically propagate into the model, right?
You could do it that way. You could absolutely connect it that way. This is much the same, right? The reason we use it this way is because it's what's a good example? Because it's a database, it means that if you change this data in the original data source, it ripples through, just like you're saying, material layers and assemblies automatically. So that data is always flowing through. There's a single source of the data, and then it's connected or bridged over to all the various tables that it shows up in. But you could do it with a local CSV. You could do it with an Excel file. You could do it with a Google Sheet. You could do it with Airtable. You could do it with Smart Sheets. You could connect almost anything into your Grasshopper as the source of the data, which is super powerful and really, really effective. So Molly wants more examples of it. Yes, absolutely, Molly. Andreas and I have a notion to build out a better course where we show a multifamily building. We've just had trouble finding anyone with a multifamily building that will allow us to use it as the base case. People are understandably skittish about allowing us to model their buildings. And so we've had trouble finding one. But we are working on that. We're trying to find a good example case that we can use for an in-depth series of tutorials on multifamily or non-residential building. It's hard. We want to try and find one that's like not too formally complicated, but it's complicated enough. So anyway, we're working on it, and hopefully we can come up with a nice tutorial series at some point in the near future where we can go through all of this detailed, non-residential or multifamily workflow, because it is very different than single family. That's a good point.
Yeah, I think with that said, I would like to thank Ed for the course today. I really thought as an introduction, it became clear to me that of course that Rhino kind of model makes sense for larger buildings, right? Once you talk about large complex buildings, managing all that data and make it flow through makes a lot of sense. So hopefully we find a good example building, and then we'll build out that course, and then everyone can learn more about that fantastic system here.
Hopefully soon. Absolutely. Thanks everybody for being here. I hope it was useful. Hope it was helpful. Hope it was interesting. And if you have questions, reach out. Always happy to discuss. As I said, if you're interested in any of the tools, go to passivehousetools.com and you can download them there and give them a whirl.
Thanks, everyone.